So now we want to look at a bandpass filter design. In this bandpass filter design, we're told we want to design a bandpass filter. We want omega C1 to be 1000 radians per second, so that's good. We don't have to convert. We want omega C2 to be 5000 radians per second. And we are told that we have use a 1 microfarad capacitor. Okay, so the first thing I want to do before we do anything else is let's review what the equations look like. So we have these equations, omega C1 and omega C2, and I'll just write them as a single equation. We do a minus or plus R over 2L plus the square root of R over 2L squared plus 1 over LC. And I'm sorry, this is, I believe the problem did specify to design a series RLC filter. So these are the equations for series RLC. So these are the two cutoffs, the lower taking the negative sign, the higher taking positive sign. So the temptation is to say, well, we know we want a 1 microfarad capacitor. So let's take omega C1 and make that equal to 1000 and plug in 1 microfarad per C. And then let's take omega C2 and make that into 5000 and plug in 1 microfarad per C. And gosh, then I will have two equations and two unknowns. But they actually turn out to be rather hard to solve. They'll be quadratics, and you'll be trying to solve for R and L. So rather than trying to do this the hard way, let's think about what some of the other properties are that we have. So I know that omega naught is the square root of omega C1 omega C2. It's the geometric mean. And I know that also that's equal to the square root of 1 over LC. So it looks like it would be easier, given C, to do our design around the bandwidth, because that's just a simple solution for L. Or I'm sorry, around the center frequency. I think I said bandwidth earlier. So we're going to do this around the center frequency because we have a simple equation for that. So the square root of 1000 times 5000 is going to equal 1 over the square root of L, which is an unknown, and C, which is 1 times 10 to the minus 6. So if we simplify that a little bit, this is the square root of 5 on the left-hand side times 10 to the third, pulling a 10 to the 6th out of the square root, is equal to, actually, you know what? Probably be easier just to square both sides. So let's square both sides. So the left-hand side is 5 times 10 to the 6th. The right-hand side is 1 over L, 1 times 10 to the minus 6. So multiplying both sides through times L and getting rid of the 5 times 10 to the minus 6, so we'll invert the equation. L should be equal to 1 over 5 times 10 to the 6th, 1 times 10 to the minus 6th, and so that simplifies to 0.2 henries. Okay, so that gives us L, and what we have remaining is we have remaining R. So beta, the bandwidth, is defined as omega C2 minus omega C1. So in this problem, that's going to be 4,000 radians per second. And for a series RLC, that's equal to R over L. That was one of the things we defined. So we now have L. So 4,000 times 0.2 is equal to R, so R is 800 ohms. Okay, so now let's sketch the circuit for that. So this is our passive RLC series. So our input is across all three of the elements. Our output is going to be taken over our R, which is 800 ohms. The capacitor, what is the capacitor? 1 microfarad. And the inductor, 0.2 Henry. Now the transfer function. So I can either plug in the components, the R over L and the 1 over R over 2L and the 1 over the square root of LC, or 1 over LC to get that, or I can realize that the general equation is that H is beta S over S squared plus beta S plus omega naught squared. And I can just use the already calculated values for beta and omega naught. So if I do that, beta was 4,000. And omega naught was what? Was the square root of 5 times 10 to the minus 6, or 5 times 10 to the 6th. So omega naught would be this quantity squared, which is just 5 times 10 to the 6th. So once again, this is omega naught squared, this is beta. Now, if you choose to use the other form of the transfer function, which is, let me pull it up real quick. The other form is in terms of R, L, and C. It's R over L, S squared plus R over L, S plus 1 over LC. If you do this and you plug in your values of R, L, and C and you didn't make any algebra errors, you should get exactly the same transfer function. So this is a little bit like AC power kind of thing, where you have multiple avenues to get to the right answer. You have different equations. There tends to be an easier way and a more complicated way. So trying to illustrate for you what the easier way would be. Okay, so that is the passive RLC bandpass filter. And the correct version of the transfer function is not this, okay, because that's unknowns, and this is a design problem, so we actually are looking for numbers. So the actual answer that a person should give is this one right here that includes numbers plugged in for beta and omega naught squared. All right, well now let's talk a little bit about an active filter design of a bandpass filter. So the nice thing about op-amp circuits is because of the infinite input impedance of an op-amp, you can cascade circuits. So if I put a high pass and a low pass in series, and I've actually drawn them backwards. I put the low pass first. So this filter is the low pass, and this filter is the high pass. So this one, so I'm going to put R, LP, and remember C is already given, it's 1 microfarad. And then I'll put R, HP. And the transfer functions for this one, H of S is omega low pass over S plus omega low pass. And this one, let's put it up high pass is omega high pass over S plus omega high pass. Okay, now in transfer functions and in cascading op amps together, H of the bandpass filter, because they're cascaded together, we can actually take the, oh sorry, I made a big mistake here. On this high pass, we have to have an S in the numerator. Okay. All right, so once again, on these bandpass filters, or on these filters, we can, when we cascade them, the net transfer function is the product. So bandpass is actually H of the low pass of S times H of the high pass of S. Okay, so we get the product. Because remember, convolution in the time domain is multiplication in the Laplace domain. So that's the whole reason for going to this Laplace type approach. Okay, so now let's talk about what this is actually doing. So if I look, as you know, a low pass filter basically passes, and we're not doing Bode plots, we're just doing sketches of, sorry, that's not going to go below 0. We're just doing sketches of H. Let me redo him where he approaches this a little more slowly. So this is what our H of the low pass looks like. Our band pass, I'm going to draw in blue. I'm sorry, our high pass. So your high pass, remember you start at 0, and then you come up. So this is the high pass, and those are magnitudes. So if I multiply these two together, then what I'm going to get, and I don't have a great scale going here. So this is 1, and it's going to multiply this, and then when they get to the point where they're both close to 1, I'll have a result that's close to 1, and then when this guy starts to roll off, then I'm going to go again, and this is not a great, I'm not doing a great job of drawing this here, but I think you kind of get the picture that the 0 part of the high pass filter at low frequencies zeroes out the low pass filter, and vice versa. As the low pass filter goes to 0 on the high frequencies, this is omega, then the low pass will zero out these values of the signal coming from the high pass filter. So there's some region in between where both the high pass and the low pass are active, as long as the cutoff frequency of the low pass filter is greater than the cutoff frequency of the high pass filter. So this is the number one mistake that people have in designing a bandpass filter is intuitively when you hear low pass you think lower, but the lower cutoff frequency actually has to be on the high pass filter. So we want our omega low pass in this design to be our 5,000? Forgot what our specs were. 5,000 radians per second. And we want omega high pass to be the lower cutoff. So we want it to be the 1,000 radians per second. Okay, so all we really have to do is choose R appropriately. And back to black ink here. So we want 1 over R of the low pass times our 1 microfarad to be 5,000. And we want 1 over R of the high pass times 1 microfarad to be 1,000. So since we got a bunch of 1s here, we'll solve for this one. So R high pass is 1 over 1 times 10 to the minus 6, and then this 1,000 would be a 10 to the third. So R for the high pass, if I'm doing my calculations correct, is 1 kiloohm. And R for the low pass will be 1 over 1 times 10 to the minus 6 over 5,000, which is 5 times 10 to the third. So that actually would be 0.2 kiloohms, or 200 ohms. So now your transfer function looks like the product of these guys, and you know your omega low pass is 5,000. So if we multiply those two together, this is what that looks like. Okay, so hang on. Yes, this is correct. Okay, so that's your transfer function. Once again, let me emphasize on an exam, I'm looking for numbers. Notice I've not multiplied out. That is okay. I do not need at this point to multiply out that denominator. I could if I wanted to. However, let me show you something, okay? We designed exactly, so this is for your active. Let's go back on that passive. Same specs, okay, based on upper and lower cutoffs. The passive transfer function was beta s, so it was 4,000 s, and then it was, let's see, let's come back here, s squared plus 4,000 s plus 5 times 10 to the 6. So s squared okay, so notice that these are not the same. So the active bandpass filter and the passive bandpass filter do not have the same transfer functions. Remember, H passive was beta s over s squared plus beta s plus omega naught squared. The active transfer function, if you multiply 1 over RC over S plus 1 over RC, and let's call that omega 1 or omega 2, because remember the low pass is the higher cutoff. So omega C2 over S plus omega C2 times S over S plus omega C1. If we multiply that together, we get omega C2 S squared plus omega C2 plus omega C1 S plus omega C2 omega C1. So this is just the algebra associated with multiplying the active high pass and the active low pass. So here's your active filter, here's your passive filter, your passive RLC. Both are bandpass filters. The only way the active filter approximates the passive filter, remember beta is omega C2 minus omega C1. And the only way that that this is possible is if omega C1 is, or omega C2 is much, much greater than omega C1. If that's the case, then this term becomes approximately beta this term becomes approximately beta. So you can't use this transfer function for the passive filter to get a transfer function for an active filter, except under certain circumstances. Okay, and so you cannot make the assumption that you can use this generic form of the passive filter to describe the transfer function of the active filter. So here's the transfer function in variables. Here's the transfer function in numbers for the active. Where is my passive? Here's the transfer function in numbers for the passive. Okay. So that concludes some examples on the bandpass filter and bandpass filter design. As some commentary, you could be given other specs, okay? You could be given specs instead of, in this problem, we gave specs on omega C1 and omega C2. You could be given specs on beta and Q. Okay, in that case, you would start with your beta and your Q. You would then figure out, this would be for the passive. For the active, you could be given a specification on the bandwidth and on one of the cutoffs. And then you would calculate the other quantities. So my sort of guidelines to you is you need to get all of your equations in front of you, as well as all of your types of circuits, and then figure out which are the most straightforward for calculating the required resistor, inductor, and capacitor values. One of them will have to be given. The other two are calculated based on specs if it's a design problem. If all three are given, then it's not a design problem, it's an analysis problem. So you can calculate bandwidth, etc. from what's given, and that would be the other type of problem. The design problems and coming up with values of R and L are slightly more challenging, so that's why I chose to work the example on that particular one. The other thing you could be asked to do is you could be asked to design an active bandpass with a gain. And we'll just put it in terms of ratio. We won't put it in dB at this point. So in that case, you would have your low pass filter, just like what we designed above, and a high pass filter. And it's highly recommended to design these two with a gain of 1. And then from there, you design a single resistor-based op-amp circuit, inverting amplifier, inverting. So let's change that. You know, it just seems intuitively that plus should be on the top, doesn't it? Okay, here, this is going to give you a gain of RF over RI. Just to review in dB, the gain in dB is 20 times the log of, in this case, 10, and it's log base 10, so 20 times the log of 10, so that would give you the gain in dB. Okay, I'm going to conclude this lecture now, and that